Hello everyone, Namaskar, Sawadika. Welcome you all to the Roto-Molding research, a special session by the TechnoBiz to focusing on the developments in Roto-Molding research and innovations. The objective of this Roto-Molding research program is to bridge a platform between researchers and industries to learn about what is going on in the university level research. So that is the main object of this Roto-Molding research program. Today, we have Dr. Alex Pritchard from Queen's University, Belfast. We'll be giving a presentation on the Roto-Molding research and innovations at the Queen University, Belfast. As many of you know, Belfast is famous for the Roto-Molding. So we have Dr. Alex Pritchard who will be giving a presentation. Before he will going to make a presentation, let me introduce a little bit about the TechnoBiz and what kind of activities we are doing for the Roto-Molding industry. TechnoBiz is started in 2005 and established in Thailand, Bangkok. We are actually recognized as international resource center for the industries and technologies, and the foundation of TechnoBiz is on the professional education, and then we expand into various business services. You can find all the information about TechnoBiz at technobiz.org. When it comes to services, we have exhibitions, training, conferences, webinars, business networks, publications, and also consulting services. So these are our services are pretty much global, and we are not only in the plastics, but we have in the rubber industry, plastics, polyurethane, adhesive coatings, and also non-polymer side and energy environment, water and environmental membrane technologies and process industries. So these are the business focus we have. When it comes to the Roto-Molding, what we are offering our services are, first of all, I would like to introduce about our exhibition, Roto-Molding Trade Expo. This focusing for the business purpose, networking purpose, all the machineries, supply chain of Roto-Molding industry, and also the product molders can exhibit in this show. We have two places next year. One is in Bangkok, 29 to 31st March, and it is going to be Southeast Asia Roto-Molding Trade Expo. And also we have Middle East Roto-Molding Trade Expo, which is scheduled in the November 2023 next year, during the 21st to 22nd in Sharjah, which is located near to Dubai. We are offering, various booth packages. They're affordable, okay, and a lot of not only exhibiting along with the exhibition booth, but we also have a lot of privileges for the exhibitors to promote and publicize their businesses. We have other service we offer is a Roto-Molding Masterclass. We have developed a 2-day masterclass with Mr. Martin Spencer, focusing on the Roto-Molding technology and practice. This is a 10-module program, 2-day long, covering the A to Z about the Roto-Molding from basics, machinery, processing, quality control, product design, troubleshooting areas, and then also advanced technologies as well. Our upcoming schedule is on the 18th to 19th October. Welcome you all to register this masterclass on Roto-Molding. Along with the Roto-Molding Masterclass, we also have the plant audits service where it has a blending with the training and also auditing. And so if anybody interested, we can offer this service as well. And we do have this biannual program, Roto-Molding Business Forum. This is basically an online event, but focusing on what is the new technologies or new developments in the market for the Roto-Molding industry. We have scheduled the third edition is on the 7th of December. They have a sponsorship opportunities out there. Feel free to check the details. And other one of the key event of TechnoBiz is Roto-Molding Leadership. This is, we having conversation with the leaders, eminent persons in the Roto-Molding industry. They'll be sharing their experiences and the lessons learned they learn, over their huge, years of involvement in the industry. It is basically simply an MBA mini class for the roto-molding professionals to learn about the leadership and also relate to the roto-molding industry. We have done a couple of sessions already with various specialists. Feel free to check in our TechnoBiz channel on YouTube. And these are, all of them are well experienced from the different parts of the world. Each country has a different way of dealing things. So I welcome you all to participate on a regular basis. We planned it once a month. Okay, some months are skipped, but mostly at least 10 sessions a year. We planned this roto-molding leadership. And of course, today is talking about research. This is one of the researches. I think everybody knows research is an important component of any business development or sustainability of the industry. So we want to reach out to researchers to publicize their work to the industry so that they understand what is going on in the industry point of view and a research point of view, and also exploring the cooperation between industry and researcher. That's an ultimate objective of this research program. Today we have the Dr. Alex with us, and of course we have this newsletter every week. We for the LinkedIn I introduce, and we have this Roto-Molding Business Connect program, which we promote, brand the companies, the technologies via TechnoBiz digital platform. So all these activities are online. So I think many of you are subscribed already our programs. It's actually 1,000+ professionals across the world been following our programs. And so, and if you're interested in it, we offer sponsorships for various programs. Feel free to reach out to me. And we are active in these social media, whether it's Facebook or LinkedIn or Twitter or even the WhatsApp groups. So be part of it so that you get updated. Yeah. And I encourage you all. There are a lot of useful information that we post on YouTube in the TechnoBiz channel, and feel free to check it out whenever it's convenient. There we have leadership, so we have business forums, and also like today's research also will be available on at the TechnoBiz channel to view at your convenience if you're unable to join the live session. Okay. I'm pleased to invite you all to participate in the activities of the STAR, Society of Asian Roto-Molders. There's our strategic partnership we have with STAR. They're organizing the annual event, annual conference next year during the 28th to 30th January in New Delhi. They do have a conference, workshops, trade expo, and also a lot of networking events. I welcome you all to participate STAR event in January next year. And if you can always check more information about it at starasia.org, or you reach out to their, by email at info@star.asia, starasia.org. That's me. If you need more information about TechnoBiz or anything that we can assist you, please reach out to me, and I'm happy to address those issues what you have. Okay. So that's all about the TechnoBiz. Before let me invite Alex to make a presentation now on the research and innovations at the Queen's University, Belfast.
Okay, hello everyone. Thank you very much for the kind introduction there from Paran. As it's already been said, my name is Dr. Alex Pritchard. I'm from the Queen's University of Belfast, based at the Polymer Processing Research Centre. And before I start, I just thought it would be useful to give a bit of background as to who I am and what I've been doing for the past few years. So I joined Queen's University in 2012, and I did my master's degree in product design at Queen's. And 4 and a bit years ago, I then moved into do a PhD in rotational molding. I finished that, and whilst at the same time as doing that, I was also for the last 18 months involved in hydrogen tank development work at Queen's University, and I'm now employed as a postdoc researcher on hydrogen tank development. And that is with my supervisor, Dr. Peter Martin. So what I'm going to talk to you about today is some of the ongoing research that's happening at Queen's. I'm going to talk a little bit about my own research, and then I'm also going to highlight some of my colleagues' research that's going on as well, and try and explain as in-depth as I can what it is that they're trying to do, but it's obviously not my specialist area, so I may have to direct some of the questions to them at the end. So to give you an idea, perhaps maybe you're not familiar, Queen's University of Belfast is based in Northern Ireland, part of the United Kingdom. This is a School of Mechanical and Aerospace Engineering building, taken on a particularly sunny day in Northern Ireland, which doesn't happen too often. And the Polymer Processing Research Centre was set up in 1996. As a side note, I was 3 at this point. It was set up to improve research and development capabilities for the Northern Ireland plastics industry, and it expands the research activities that happen in the QUB Mechanical Engineering department as a whole. And we have a range of undergraduate and postgraduate courses for the students. And the PPRC itself also acts as a training facility for the Northern Ireland plastics industry. We have 7 permanent core staff of engineers and researchers who are employed in the PPRC, and we can offer a range of training programs, consultancy and joint technology transfer programs where so a student would be based in a company but would have access to the PPRC facilities to be able to transfer knowledge from the PPRC out into industry. We're very good at creating desktop studies. Obviously, miniaturizing industrial scale processes is fairly handy for research purposes. It can take quite a while to do industrial scale process trials. Although we do also have equipment for that, and I'm going to give you an idea of the equipment we have available. We have approximately £2 million worth of equipment within the PPRC, covering 400 meters squared of modern laboratories. And this gives you an idea of some of the facilities we have. So we have expertise in extrusion, thermoforming, compounding, injection stretch blow molding, and then into material characterization and injection molding as well. And then in addition to that, we have the rotational molding capability. So our lab is equipped with a ferry machine, which you can see a very artistic picture of that to the right-hand side here. The industry as a whole we see is moving towards direct electrical heating, and we have an AMS robot system installed in our lab that I'm going to talk about in the presentation. We also have a wet coat grinding facility, which enables us to couple then with the extrusion processes to be able to look at like recycled material and its use in rotational molding. We can do a lot of particle analysis, so we have sieve shakers and polymer melt imaging systems. And then in addition to that, we have equipment for monitoring temperature, both on the electronically heated molds and in the gas-powered systems as well. So rotational molding within Queen's stems quite a few different research themes, and a lot of these themes overlap between each other. So I'm going to try and summarize the main categories. My involvement has mainly been on foam structures and in process control and monitoring. But I'm going to also talk about my colleagues' research in composite structures and simulation and recycling. So to begin with, we're going to look at the foam structures. So for my PhD research, I had an aim to investigate and optimize large-scale, lightweight, multi-layer structures. These were targeted at offshore wave energy generation devices, of which there's an example on the right-hand side of this slide. And that could either be in the form of skin foam or skin foam skin. Now, one of the problems that I had identified early on in the project was that in order to optimize these foam structures, it would be incredibly difficult to do a trial and error type exercise of trying to optimize them in industrial scale equipment using our very roto speed machine. So instead, what I started to explore was this miniaturization. So looking at either small scale or offline experimentation techniques. The limitations, obviously, of using full-scale equipment are that you're going to use large amounts of equipment, and it can take quite a while to produce, even just a foam-only molding. On the other hand, the hot stage microscope systems, because you're imaging the polymer melt as the foam grows, as the bubbles grow in size, the microscopes at a certain point then, when the bubbles start to merge together, don't really give you that much information. And that means then that you can't observe the global growth behavior of your foam. So I went down the path of trying to observe this global foam behavior. And you can see the iterations that I had been through to be able to get to my final experimental setup. So we started with an oil bath, and that moved into a glass oil bath, which enabled me to image through the cross section to be able to get the foam height change. And that then was taken a step further to a bit more of a scientific, digitally controlled setup, where I was able to maintain accurately the temperature of the oil bath. The advantages of this were that in my particular case, it only needed 5 grams of material instead of probably around 2 to 3 kilos of material for a small cube mold on the ferry machine. It also meant that you could scale up the experiment so that you could make multiple samples under the same heating conditions if you wanted to. And because it was digitally controlled, you were able to create a comparison between the industrial scale equipment and my experiment. So just briefly, because this video isn't going to show very well, so what I have is 2 oil baths. One is providing the heating, and one is providing a controlled cooling rate. And what happens during this is, so this is the view that the camera sees. The test tube's lowered into the heating side, and over a period of time, the polymer starts to compact as it melts, and then eventually starts to expand as the blowing agent activates. In this image here, that then gets moved across to the right-hand side, and you can see the temperature reduction of the melt in that image on this side of the trace. And this then gives you the shrinkage of the foam during the cooling process. So from the images that were captured, roughly about 1 every 20 seconds was sufficient to capture the data that I needed. The images were imported into some software called MyPar, which automatically cropped the region of interest, so the red box in this case, in each image, and it exported the height of the box in the y-axis, which gave me then the foam height change. So I've got a couple of examples to demonstrate what that shows. So in this case, it's the effect of chemical blowing agent concentration, which is a fairly standard thing to adjust to get a thicker foam. And you can see on the graph here that there's barely any change during the first 5 minutes. Towards 10 minutes then there's a dramatic increase in the foam height, and that increasing in percentage of blowing agent gives you an increase in the foam height. Interestingly, it allows you to experiment with things that you wouldn't ordinarily be able to in an industrial scale without significant effort. So in this case, what I'm showing is the effect of polymer particle size on the foam height produced. And you can see that at 425 to 500 microns, you get a foam down here. But at 90 to 106, a much finer particle size, you get a sharp increase between the two in the foam height, and equally a reduction in the foam density that's produced. So that might suggest then that a finer particle size produces a more optimum foam, smaller bubbles, and more of them. So at the same time as doing that, it became obvious that there was a relationship between the sintering and densification behavior, the bubbles that are trapped within the polymer melt itself. So I developed an experiment where I have a glass plate and a little jig to put the polymer powder into. And let me see whether I can find it. So that little jig is filled with a polymer powder, and the jig is then removed. That plate is then placed inside this contraption with a glass viewing window, and the little polymer powder plate is in the bottom of this chamber. That then gets set up on this hot plate over here. And what we have is a camera with a light that is shining down through the glass, looking onto the polymer melt. You can see that on the PC to the right-hand side here. And what I have over this side is a vacuum pump, so I'm able to experiment with the pressure and its effects on the polymer melt instead of controlling the densification behavior using particle size. So I'm going to explain that a little bit more in the pictures that are captured during the experiment. So the first set of pictures here is for an experiment on a standard rotational molding powder not done under any pressure. And you can see that polymer melt forms and these bubbles remain fairly constant in size through the duration of the experiment. If you then do the same thing under a vacuum from the start, and then remove the vacuum, so from this point to that point, the vacuum has been removed, you can see there is a dramatic size reduction in those bubbles, and eventually then you end up with no bubbles. So that's a pretty easy way of removing the bubbles from these polymer melts. The next thing then that you can do, interestingly from a foam point of view, is you can pull a vacuum after the bubbles have been formed, and you can get them to grow in size like that. I'll just show that again. So no vacuum with a vacuum, and that is a nice way of producing a foamed rotational molding without using any chemical blowing agents. And you can change the pressure to be able to control the bubble size, which is something you wouldn't be able to do with a chemical blowing agent. So I have a chapter in my thesis on optimizing that as well. So the next thing I want to talk about then is controlling fiber reinforced rotationally molded parts. So this work has been done by David Castellanos. He started down the route of looking at thermoplastic fibers for reinforced rotational molded parts because of the good resistance, high compatibility with the polymers that are used, and for recyclability. So that's a typical image of a composite mat that he would have been looking at. And the question he was trying to answer was, are they suitable for rotational molding? And the way that he went about trying to identify this was doing some characterization. So one of the first experiments that he did was to put this inside of an oven and incrementally increase the temperature of the oven and take an image of the composite plate to understand how it changed at temperature. And from that, he selected a number of candidates that looked to be suitable. And he then placed them manually into a rotationally molded polymer melt by opening the mold during the molding cycle. So he reversed it out of the oven, took the mold apart and placed this fiber into the polymer melt and then returned it back into the oven. You can see though that there's sort of variable results with doing that because of the manual placement, and in some cases, if it doesn't fully get embedded within the polyethylene in this case, and then other areas can end up being deeper. So it's not a very controllable process. He then went on to understand the relationship between the bubbles, the pinholes that remained within the polymer melt after you put in the composite reinforcement. So he was using the same technique that I was using to monitor bubble sizes in polymer melts. And here's an example of what that would have looked like. So on the left-hand side, you've got the bubbles in just a standard rotational molded polymer melt. And on the right-hand side, you've got bubbles that are suspended above the composite reinforcement. So there was some work involved in trying to optimize that to make sure that the pinholes were removed during the cycle. The other thing then that he was looking at was trying to understand how the polymer was absorbed into the fiber itself. This process is known as a wetting process, and you want to encourage the wetting process to be able to get the fibers to be well embedded within the polyethylene matrix itself. And one of the conclusions that he came to after doing all of that process was that it's actually easier to produce preforms by compression molding the composite into a polyethylene bed, first of all. And this is an example of what that looks like. So you've got the polyethylene matrix itself, which is well compressed within the composite material itself. And he then went through a series of iterations to try and perfect which material gave the better mechanical properties. And in most cases, he was finding that by placing that material into a rotationally molded part as a preform, he was getting consistent mechanical improvements. Mechanical performance improvements. So we also have another colleague, Jitendra Sarigar, who's working on the rotational molding simulation side of things. And his research interest has moved into the effects of shrinkage and warpage and how we model that. So shrinkage and warpage is affected by the uneven cooling of the part, either from the external or internal face, depending on whether you're doing external or internal water cooling, for example, or air cooling for that matter. And depending on what direction the cooling rate is moving in, you get a compressive force on the part, which then creates this air gap. And he is able to simulate the temperature change across the mold, which then can be translated into a warpage plot of these parts. So in this case, what you're seeing is a rapid external cooling effect, which was a spray of water onto the surface. and he's able to plot down the displacement of the parts, and in this case he's gotten a 2.12 millimeter deflection. But equally then you can simulate the effects of rapid internal cooling, which is something that is extremely beneficial to rotational molding. From a research perspective, it could really cut down on cycle times, but from an industrial perspective, it's incredibly difficult to be able to implement internal water cooling and control it effectively. So this research then, we hope, is going to progress towards being able to perhaps balance an internal and external water cooling process and be able to optimize that displacement and minimize the warpage of the parts. So finally, I want to discuss some of the future rotational molding technologies that have been developed at Queen's, and this is more of a collaborative nature. We all chip in together to be able to make use of our AMS robot, which is an electronically heated mold. And you can see there is a box on the side of the mold over here, and that has an industrial PC mounted within it, and we can get wireless access to that PC anywhere in the world. We can use that then for temperature monitoring and taking images, and we can also do ultrasound. So that's some of the things that I'm going to discuss now. So in the case of David's work, he's interested in trying to monitor the fibers within a molding. So he developed a camera system that is able to monitor the opposite wall from the camera. And this is what you see during that process. So this image is just a standard rotational molding cycle, and you can just about make out the bubbles on the surface of that molding. And then into the shrinkage and warpage phase, and you start to get a lot of reflection from the unevenness of the polymer melt as it starts to solidify. So if we take that a step further, and you then put chopped fibers into the same molding, what you start to see is at the early stages, there's fibers sort of passing by the camera but not sticking to the mold because it's not hot enough yet. But at a certain point, layer by layer, the polymer starts to stick to the mold, and you can see that some fibers start to get captured within that polymer melt. And iteratively, then you get a layer after layer buildup of polymer with chopped fiber. So he's been able to use this to identify things like how many fibers were stuck onto that polymer wall, and the orientation and layout of those fibers within the image, which can then go to optimizing things like the robot movement to be able to control where those fibers are placed. So at the same time as doing that, I had developed a system for monitoring the vacuum foamed samples. So pulling a vacuum on a polymer melt that has bubbles already existing in it to create larger bubbles. So the same idea applies here, and you get this polymer melt that builds up on the wall. And then at this moment, you can pull a vacuum and you can see those bubbles start to increase in size. Now this happens fairly slowly because of the size of the mold and the size of the vacuum line that we were using on this machine. And then it moves into the solidification phase. But one of the nice things about that is that unlike using a chemical blowing agent process, you could get the robot program the robot so that you could have, for example, an input window that says what average bubble size do you want to see in your molding. So you could put 100 micron in this, and it would then control the pressure line to make sure that the average bubble size within the image that it was analyzing was within that region, which is something that you just wouldn't be able to do with a chemical blowing agent system. So in addition to that, another student, Haitian Zhu, is looking at the robot motion. So one of the benefits of using a robot system is you have the possibility to do these freestyle motions, making use of all 6 axes of the robot. At the moment, I think we're using 2 axes, maybe 3 sometimes. So his research is trying to answer what are the benefits from doing that. At the same time as doing that, he's also looking at how does the speed affect the moldings. So he's using a uniaxial machine to try and simplify his experiments, and he's making comparisons between, in this case, 10 RPM and 38 RPM, the speed of rotation of the mold itself. And some of his early work has indicated that the rotation speed does have an effect on the bubbles, and you can see that increasing from 50 to 300 rotations per minute dramatically reduces the amount of bubbles that are present in the mold taken from an image at the same point in the cycle. And then lastly, I want to discuss the use of ultrasound in rotational molding. Now, perhaps some of you are aware that ultrasound can be used for monitoring polymer thickness of molded products that you've demolded and have been sitting around on the factory floor for a while. What I was interested in, though, was how can we use ultrasound to be able to monitor what the polymer is doing inside the mold during the rotational molding cycle. So over the 4 years that I was doing my PhD, I was looking at applying an ultrasound transducer, which is this T1 signal, onto the wall of a mold, which is M1 to M3, because you get returning echoes from the sound wave that's produced from the transducer. And there's also an element of the sound that passes through the polymer and reflects back again. So in the graph underneath here, what you can see is this T1, which is what we call the initial bang, which is the returning signal from the end of the ultrasound transducer. The sound wave then passes through into the mold wall, and you get a returning echo M1, M2, and M3. If you place a polymer plate on the back of that mold wall, there is a signal identified, which is these little numbers here that sort of increased in time across the graph. So the initial indications were that you could indeed see the polymer on the back face of the mold, and not only that, you could pick up the thickness of the polymer sheet that's placed on the back face of the mold. So I took that a step further, and I did a 1 kilo molding on a tank mold, which is the one that you saw in the picture previously. And what you can see is that during the cycles, so at time 0, and then the gray line up here is at the end of the cycle, there is a peak that appears during the heating cycle, and then it slowly shifts back to the left during the cooling cycle. And it would appear that that is the polymer thickness itself, and you could measure between these peaks and work out what that thickness is. But more interestingly than that, you can also monitor the amplitude of these signals, the strength of the signal that is returned back to the transducer. So if you imagine taking, for example, the peak of this signal right here and plotting how that changes between all of these curves, what you get is a graph that looks like this. So during the heating cycle, for an empty molding, you get this blue trace. And if you make a 1 kilo molding, you get the gray trace. And if you make, you get the orange trace. And if you make a 2 kilo molding, you get the gray trace. And what this graph shows then is the onset of the adhesion, the point at which the melting is completed, the effects of the thickness on the returning signal. And you can imagine this by if you were to ring a bell and then place a damp sponge onto it, the harder you push the sponge, or the more sound absorbing the sponge is, the more sound is going to be absorbed and the less ringing the bell is going to do. And that's what this graph is showing. So the 2 kilo molding absorbs more sound, and therefore the amplitude of that signal is reduced. And the same thing then during the cooling cycle. You don't really see too much change, which you would expect, until the solidification is complete. And it looks as though something was going on at this point. And then towards the end of the cycle, in and around 100 degrees, there's this return of the amplitude of the signal, which returns back to this blue trace. And you can imagine that as though you are removing the sponge from the bell, or in this case, you're removing the plastic from the surface of the metal, and that sound wave then increases in amplitude, and you get all of your ringing back again. And interestingly, that then shows the shrinkage, and this point shows the warpage and how the molding is changing. So it started to release, and then a different area of the molding then changed shape, and it then made contact with the mold again to dampen the sound signal. So that's a fleeting glimpse of the research that's going on at Queen's University. And I'd like to thank you very much for your attention, and I'm more than happy to take questions, because I'm sure you've got endless questions on this.
Thanks a lot, Alex. It's an excellent presentation as you give us, what's going on at the Queen's University. Now I invite Martin Spencer to take over for the discussion session. Before Martin starts, I'd like to convey sincere thanks to Mark Hiens. Because of him only, we were able to bring Alex for this session. Special thanks to Mark Hiens and also all the team at the Queen's University Belfast for supporting this roto-molding research. Martin, over to you.
Okay, hi. I will start some of my questions, and obviously we're inviting questions from the audience if you want to send them through to PRAM, and I can pass them on to Alex once we've done that. In the research that you were doing, Alex, did you try a variety of different blowing agents at different temperatures? And were the blowing agents you used all exothermic, or did you try endothermic agents too?
That's a really interesting question. There are a number of reasons as to the difficulties involved in that. So I think I had about 8 different candidates for blowing agents, a mixture of endothermic and exothermic. For obvious reasons, the endothermic ones are slightly more difficult because you've got to keep putting energy into the system to get them to blow. So pretty early on, they were ruled out as not really appropriate for optimizing the foam structure at that time. And what I was left with then were the exothermic blowing agents. Of the exothermic blowing agents, most of them were in and around 170 degrees Celsius. Most were OBSH based, and there were a couple of AZs, but the blowing temperature were too high. It was like in the 200 degrees, 220 degrees. So you're looking more at a nylon material at that point, and I was more interested in polyethylenes based on the test tube experiments. I had a temperature limit to keep with them.
Okay, do you think there's any relationship between the type of blowing agent you use and its effect on the particle size? You know, you were saying that you saw a more blow in smaller particle size. Do you think that would change by using different blowing agents?
Certainly the foam height would change. The interesting thing in those graphs, though, were that the blowing agent was consistent between those samples.
Right.
I would imagine that you would find the same trend if you were to repeat that experiment with a different blowing agent, but certainly the foam height results themselves would not be comparable, if that makes sense.
Okay, yeah. So, but you didn't actually try different blowing agents with different particle sizes. You stuck to one blowing agent, did you? For your...
I tried 3 blowing agents.
Right.
The 3 that I tried, the results were fairly consistent between them because they all had roughly the same blowing temperature, and they were very similar materials.
Okay.
The problem with researching blowing agents is it's incredibly difficult to get small batches of blowing agents, and they're not particularly pleasant to ship around the world.
Yeah, I appreciate that. So, I mean, that brings us to the interesting discovery you found on changes in pressure, being able to produce a foam without blowing agents. When you were using a vacuum, did you find that it was the time you applied the vacuum, or how long you applied the vacuum for, that was changing the bubble sizes?
Both had an effect. Both had an effect. The timing is really important to get right, and to be able to optimize that process, what you need is a really high heating rate to be able to encourage the bubbles to stay around from the sintering process. You need them to stay around long enough to be able to pull the vacuum at the end. So high heating rate and timing is critical to get that application right.
If you wanted to blow it more, you could leave the vacuum on for longer, or is it a pressure thing as well? Do you use a different amount of vacuum?
Just turn the vacuum up.
Right. Yeah.
Yeah.
For the same amount of time, so you just have a higher vacuum for the same amount of time rather than using the low vacuum for a longer time.
Yeah. Yeah. And the interesting thing is that it's a dynamic process. So using the camera system, if you were monitoring it, if you just turn the pressure down, you'll reduce the size. If you turn it up, it'll increase in size. Okay.
And then your colleague who was doing the trying to put the woven textiles into, did he try using vacuum as well when he was doing that, or pressure for that amount? Whether a vacuum or pressure or a combination of both, maybe cycling between the two might have an effect when you're trying to incorporate fibers.
Interesting question. I don't recall whether he did actually try pressure. His research sort of led itself into how do you control the placement of those fibers in a more controllable manner.
Yeah.
So the pressure actually came in the end from an inflatable balloon that was placed inside of the mold, and that was inflated at the correct point to put the pressure up against the plate and press it into the polyethylene.
Right, and he was doing that even when he was using the pre-pregs. Yeah. Okay, and the pre-pregs were pre-pregged with polyethylene or with a different polymer?
I have a feeling I think most of them were polyethylene. He also looked at polypropylene because some of the fibers had a polypropylene outer shell that helped with the bonding between polypropylene and polypropylene. And then placing that plaque in the polyethylene, it had something to grab onto around the edges.
Okay, and also when on the research that was looking at incorporating chopped fibers, were those fibers pre-impregnated or were they just natural fibers that were being used?
They were natural, but he did look at sizing of them as well.
Right, and presumably sizing or pre-impregnating them with something is going to help with that, I would think, because from experience, unsized fibers tend to float to the surface much more easily.
Yeah. he's certainly had a lot of experience in sizing and trying to get that right. I don't know the ins and outs of it, but I think you're right in that the sized fibers did perform better in his experiments.
Right. Okay. And moving on to motion of the tool in some of the research you're looking at with the robots.
Mm-hmm.
You obviously were showing that an increase in speed was helping with bubble removal.
Mm-hmm.
Presumably the temperature was constant, was it, at that side? Because obviously normally there is quite a close relationship between the speed of rotation and the temperature of the tool.
Yeah, the temperature was held consistent between them all. It was only the rotation speed that was changing.
Presumably that's a sort of effect of, because you're rotating much faster, you're capturing less powder on each rotation and giving it a better chance to melt.
Yeah,
because obviously your powder buildup would be a lot less if you're rotating faster at the same temperature.
Mm-hmm.
Because normally if you increase the temperature in a standard rotation molding situation, you would also have to increase the speed of rotation to get similar buildup inside the tool.
Yeah,
because there is a close relationship between them. I just wondered whether any research has been done into that or not yet.
In that particular case, it's very early days. The research is only now really starting to progress.
Okay.
But I'll certainly feed that back to Hang Tian, and you know, he can take it forward as a suggestion for something to do next.
Okay, and then moving to your last subject, which was the ultrasound, really.
Mm-hmm.
Where are you with that research at the moment? How practical is that to incorporate that onto a production tool? Would it only work on direct tool heating, so electrically heated tools or oil heated tools, or do you think, have you got ultrasound equipment that will cope with temperatures in a normal oven or not?
So that is an interesting question. Ultrasound is really beneficial for rotational molding, and the results I've seen are quite promising for it. There is obviously a massive price to get over to be able to start using that technology. In my case, the ultrasound transducers were high temperature ultrasound transducers that were in and around £4,000 a piece.
Right.
They are designed for monitoring corrosion of pipes for the oil industry.
Mm-hmm.
And they can be taken up to about 700 degrees Celsius at the tip end of the transducer itself. So theoretically, you could place it inside of a gas-powered oven and it would work in just the same way. The problem is that the cable that connects to the transducer is not high temperature, so you would need to try and find some shielding for that.
Right,
and you then back into how do you extract that signal from outside of an oven.
Yeah. So I mean, it's always, as always, a lot easier with the electrically heated or oil heated tools that don't go in and out.
Yeah, it's almost plug and play on a electronically heated tool.
Yeah, it makes life a lot easier. So, so one last question, sort of, what sort of stage are you at with hydrogen tank research, and what are you looking at? Obviously, there's a lot of people working on this around the world at the moment, and a lot of companies have started what I would probably call low volume production or prototype production of roto-molded liners for hydrogen tanks, but I still think there's a long way to go on the understanding of how the liner works in conjunction with the outer coatings and things. And are you looking at that, or are you just looking at the liners?
Outer coatings isn't part of the current project. My research at the moment is focused on the design of the boss components.
Yeah.
How to get those to better integrate within the liner itself.
Yeah, which has obviously been a problem for a lot of people doing these prototyping. Some people seem to have come up with a solution, and other people are still struggling with this, I think.
I've been at this for 3 months now, and it's tricky to get it right. The play-off between making sure you've got enough material, but not too much material that you can't keep enough heat in it to get the polymer to.
You find the material that you're making the liners out of will affect that as well.
Yeah, Yeah, it's a really tricky thing to balance. So one of the things that I'm doing is working on simulation side of things to be able to get a computer model to predict what that shape should be.
Right. Okay. So you're modelling the heating and sintering effect of the material around the boss.
Yeah. Plus, then it's mechanical locking into the polymer liner itself.
Yeah. But to get obviously that mechanical lock, you've also got to be able to get the material to flow around the boss in the first place correctly.
Yeah. Yeah.
Okay, well, I think that's bringing my questions to an end. Piram, if you've got any questions that have come in?
Yes, I have posted onto the screen. Okay, yeah.
Okay.
Alex said, for the sake of our recording, can you repeat the question and address it? Yeah, please.
Okay, I will do. So the question is, where might the rotational molding industry benefit from the use of ultrasonic process monitoring? The obvious answer for this at the moment is in the development of hydrogen tanks, actually. And in order to get the hydrogen tank to burst correctly in the right location, you would change the thickness, and you want a thinner midsection and a thicker dome end. So you would be able to use the ultrasonic process monitoring technique to be able to make sure that your polymer was in the right thickness range, not only to make sure that the tank is safe to use, but also from a gas permeation perspective, you would be able to confirm that it's got enough material there to make sure you're not going to have problems with the certification process.
Okay.
As we were saying earlier, I think it's only really going to be of complete benefit for people that are producing on electrically heated tools, because it's going to become much too difficult to use those sort of techniques in ovens, particularly if you're going to end up with multiple ultrasound devices at 4,000, 5,000 pounds a piece.
Yeah. Well, the other thing is that trying to achieve that accuracy of thickness in a gas-powered oven, I think, would be pretty tricky to get consistently right.
Yeah, I think that's right. Yeah.
When you're talking about something that could be 700 bar pressure, the safety aspect of it, I think, takes over.
Yeah.
Okay, can I move to the next one?
Okay, so the next question is, how might the composite reinforcements be applied during an industrial rotational molding cycle? And myself and Martin have just touched on this one, actually. It usually involves some sort of mechanical process, like inflating a balloon inside of the mold to be able to get the preform or your composite sheet to be embedded within the polymer melt during the cycle. If you are using direct tool heating, you might be able to use a small robot to be able to service the mold, and that would give you a controlled pressure to be able to press that sheet into place. But obviously adding a small robot to the system then increases the cost of the robot cell. Okay, and the next question then is, what benefits are there to producing foams with finer particle sizes? Which actually goes back to another thing that me and Martin were discussing there. To be able to produce an optimum foam, you need to make sure that the bubbles that you have remaining from the densification process are completely removed, because the gas that's produced during the chemical blowing agent decomposition tends to target those bubbles that are remaining and it makes them really coarse. So by using finer particle sizes, you can densify quicker, and that then means that you can look at reducing your chemical blowing agent decomposition temperature to something that is lower. And that has two benefits. You're going to lower your cycle time, and at the same time then you are increasing the melt strength, which then is resisting the growth of those bubbles. So you should end up then with a more even cell distribution through your foam.
Yeah, one of the disadvantages of using finer powder is distributing that powder around the tool, because typically if you're using a second or third shot of foam, you're adding the powder to a mold that is already hot and already has a layout with a tacky surface. So from the experience of doing that, from a distribution of powder point of view and getting the powder where you want it within the mold, it is beneficial to have a coarser grind. But obviously now this is showing that you can actually get better foam with a finer grind, and it's how to balance those two things, I think.
Yeah, the other side of this then is obviously a finer grind is going to cost more to produce.
Yeah, and certainly we found with a finer grind it would tend to clump in the mold, particularly around the areas where you were adding it through the hatch or whatever you're adding your second shot through, or around your drop box. You would tend to get clumping the finer the powder was. So the coarser the powder was, it flowed around the tool a lot more easily.
Interesting.
Maybe it's worth looking at something like micropellets for that, different sizes of micropellets to work, because they would flow around the tool a lot better than a fine powder. And you can get very, very fine micropellets that might be able to work. I don't know, but something else to look at, I suppose. I can keep coming up with lots of ideas that you should be researching, but it's finding the time and money to do these projects, isn't it?
Yeah. No, micropellets is actually not something I've experienced yet.
Yeah.
And one of the suggestions I've made in the thesis was that perhaps just using a vacuum to densify those bubbles is more cost effective than using the finer particle size in the first place.
Yeah.
Because then the particle size has no influence on it. It's all controlled by the vacuum.
Yeah.
If increasing, the next question, if increasing the axis speed can remove pinholes quicker, what speeds might be possible with a robotically controlled mold? So I have asked Hang-Tian this morning about this, and he says that our robot could theoretically, if you so wanted to, rotate the mold at 60 rotations per minute. Now, I don't know whether the school's health and safety team would ever want to see the mold rotating at that sort of speed, so there may well be an upper limit, but theoretically 60 rotations per minute would be achievable on the robot that we have in that picture.
I think on that particular question, though, I don't think, I might be wrong, but my understanding is it's not the rotation speed that is removing the pinholes or the air bubbles. It's the fact by using a higher rotation speed, you get less air bubbles in the first place.
I have a funny feeling that he was going down the route of spinning. I think one of the pictures was at 300 rotations per minute, and he was starting to take into account centrifugal forces or centripetal forces, something along those lines. I think that's where his thinking was going, but I think you're right that the lower speeds and indeed 60 rotations per minute is nowhere near 300.
Yeah.
It probably is more of a heating control process than a force control process.
Yeah, but as we were discussing earlier, I think as you increase the rotation speed, you're picking up less powder onto the surface on each rotation. So you're giving it a better chance to melt and start to sinter out before you're adding too much powder. You're not adding too much powder in one go. It's being added a little bit at a time. Whereas with a slower speed, the buildup in powder on each turn is thicker, and you're adding more powder. So therefore, entrapping more air. Potentially, I don't know. That's just how I'm thinking about it at the moment.
Yeah, no, I'm going to feed that back to Hang-Tian because it is a particularly relevant conclusion for that bit of work. I mean, it's probably not ever going to be possible to rotate something that size at 300 rotations per minute safely.
Probably is, but it will probably sort of make the machines extremely expensive.
Yeah.
To be able to do so safely. Yeah.
So at the lower speeds, I think he really needs to start thinking about the powder flow and the heating and that layer build-up that he's getting.
Mm-hmm. Okay. Do we have another question? Oh, hang on.
Yes, yeah, we do. Yeah. So this question is, do you think the relationship between rotations per minute, axis speed, and void reduction can be used to reduce heating cycle? Does this research assess to what extent gas consumption and cycle time could be reduced due to the phenomena observed? The simple answer is no, it doesn't assess the gas consumption and cycle time reduction. That actually is something that's particularly relevant though in this case, because if you're putting more energy into your robot to spin it faster, it's obviously got to have some benefit, because if the cycle time remains the same or you're using more gas as a result of it, then it obviously negates doing it in the first place. So again, that's something that I will feed back to Hang-Tian as a topic that he needs to explore. Did that answer the question in relationship? I think that answers that question.
Yeah.
Are there any more questions? Okay, so the next question is, how were the PE foams prepared? Mainly by dry blending. That's correct. They were all dry blended. Turbo Blender has a 20 kilo minimum payload on it, and I was only using 5 grams of material, so it didn't make sense to go to a turbo blending process.
And you didn't try any compounded materials, where the blowing edge has been compounded in?
No, I didn't.
Do you think
It was all. Sorry.
Do you think that might make any difference?
It would be interesting to try it, because it may well help with this particle size problem. Like, that could be another avenue of negating having to use finer particle sizes.
Yeah, because I mean, generally, again, I think if you're trying to build up a big, thick layer of foam, compounded foams tend to work a lot better than dry blended ones, unless you're using very low temperature ones, which makes the processing difficult. But for some reason, the lower the temperature of the blowing agent, trigger temperature, the easier it seems to be to dry blend. I don't know why that is. That's just from my practical experience, but seem to get quite good results with low temperature blowing agents dry blending. But as you move to the higher temperature blowing agents, such as the 170s, 180s, or whatever, then you get better results from compounded materials. But again, that's my experience, and it's probably slightly outdated now as well, because I've not actually been doing this for the last 7 or 8 years. So
it's something that's particularly relevant, because the optimization of the blending process for chemical blowing agents, I've never actually seen any research done on that. There are suggestions that if you have a bed temperature of between 60 and 70 degrees, apparently the chemical blowing agent will somehow adhere to the surface of the polymer that you're blending it with, and that's supposed to be beneficial. But again, I've never seen any research done on that particular case either. So,
but that would also tend to suggest that if you were compounding it, it would be even more beneficial, presumably.
Yeah.
But obviously, compounding is not that easy because of the temperatures that are required to compound without reaching the trigger temperature of the blowing agent.
Yeah. Plus, then you've got all of the time that it takes to be able to get the system ready to be able to compound even one of your blowing agents. From a research perspective, it just turns into a complete headache trying to produce multiple batches.
Yeah, trying to compound 5 or 10 grams at a time might be tricky.
Yeah. But the good thing about the experimental setup that I've demonstrated is that if you have ideas like that, all you need is a tiny little bit of material to be able to compare it with your previous samples.
Yeah. Do we have any more questions? Another one here.
Okay. So the next question is, did you only use one type of polymer during your foam studies? Is foaming process polymer structure dependent too? So to answer the first question, the only polymer that I have described in my thesis is polyethylene. I also looked at using nylon and polypropylene as well. The problem with that, though, was that I'm temperature limited in my experiment to 200 degrees Celsius on the heating oil side. So I couldn't get comparable results. The foaming process, though, is definitely polymer structure dependent as well.
What about the melt flows of the polyethylene we're using? Did you try different melt flow materials?
I did, yeah. So I had a series of LDPE materials that were all roughly the same. They all came from the same brand name. I think they were Latrine materials, and the MFI was between 0.8 and 70. And I used that then to explain the effects of rheology on the foams produced.
And was that effective, the amount of rise you were getting, the melt flow? Yeah,
very much so.
So the higher the melt flow, the less rise, or which way around were you experiencing?
No, other way around. The higher the melt flow, the weaker the strength of the polymer, the larger the cell sizes, and the higher the foam. Yeah,
and also presumably you've got better chance, also a more chance of it collapsing if you're using high melt flow material after it's blown. Yeah.
Absolutely, yeah. But then the 0.8 MFI material then was just it barely even sintered properly. The foam it produced was practically useless, so that there is a lower limit to that as well.
Yeah. Absolutely. General Roto-Molding, yeah.
Yeah, the conclusion is that the rotational molding standard powders actually lend themselves quite nicely to atmospheric chemical blowing agent decomposition to produce foams.
Okay.
So sorry. Oh, have we lost Martin?
Yeah, sorry. That's I was just saying the next question's on the screen if you want to.
Oh, okay. Yep. So the next question is, what advancements in rotational molding materials is required or desired for hydrogen storage applications? This isn't actually an area that I have got involved with yet, and if anybody on the call has equipment to be able to do this, I would be interested in exploring doing research with that sort of equipment. What we need is a rig that you can monitor gas permeation at 700 bar pressures, preferably with hydrogen. There is a research facility in Japan that has that capability, and I'm trying to pursue getting either some preliminary results from them or collaborating with them. But this isn't my area of research for the project that I'm on at the moment.
Okay, that's all the questions we have, Alex. Thank you very much.
That's okay.
Okay, well, I think that's been a very interesting session. Thank you very much, Alex. And it's given us an insight into some of what's going on at Belfast at the moment. I know there are lots of other research projects that we don't know anything about just yet. And we look forward to hearing about those in the future once they come to fruition. So if you'd like to just sum up for us of what you've told us about today before we bring the session to an end.
Absolutely, yeah. So I want to thank everybody first of all for attending and listening. Hopefully that's given you a pretty basic overview of what's going on at Queen's, and perhaps has given you some ideas for applications of some of the technology within your own factories. equally then it might have given you some ideas of, I don't know, projects or questions that you might want to raise with us here at Queen's, and we're always open to collaborating with industry. And if you are ever in Belfast, then let us know, and we would love to meet up and get in contact with you all. The other thing then is I would like to thank TechnoBiz and Martin Spencer for hosting the event. I think it's been pretty successful.
Okay, well, thanks very much for joining us today and giving us your time to explain this. And thanks for all the audience for joining us as well. And we look forward to welcoming you to the next Roto-Molding research session, which we will be notifying you of shortly if you watch the newsletter or online on LinkedIn, and also to our other events, our Roto-Molding leadership events, and our next seminar session, which will be in December. So thanks very much for joining us today, and thanks again, Alex. Goodbye, everybody.
Thanks, Alex. Thanks, Martin.
You're most welcome. It's my pleasure.